it's very small. But when you look at the hydrogen is 91% by number of atoms and 70% of mass, and the same for helium, which is 27%. So how do we know the abundance of elements in a star? We will know this too. First of all, you have to know that to identify the wavelength in a spectrum, there must be some very well-known lines, spectral lines. So thanks to Balmer, he identified some Balmer lines, which are H alpha, H beta, and lots of H series, which we can identify to calibrate our wave length profile of a spectrum. There are also Paschen series, there is Layman series, there are lots of series. So this is, for example, a spectrum of a star, but it's not a very real spectrum, because the continuous spectrum is not always that bright. But there are always bright lines. This is not a very real one. There will be bright lines, okay, for these emissions, okay. This part will be very, very bright because the emission is here, and this part will be not bright, so a little bit dull. And for the absorption lines, here's the Balmer absorption lines. So the more the strong, the more the absorption, the more the abundance of the element, and the more the wide, it means the more temperature or the less brightness, the less brightness. And as you say, from this spectrum, this is a very, very hot spectrum, and this is because the peak of the wavelength here, it's at the blue region, okay. So that's why this will be a hot star. And the Balmer lines can identify the temperature also of a star, the strength of the line, okay, the strength, how the line is strong. It can identify the temperature of a star, the surface temperature. We're always talking about the surface temperature. And here is no, it's not the surface temperature. This is the temperature of the element itself. Okay. Here are, for example, the ionized helium. The more strong, the less the temperature, but then when it's less, it becomes high again. But this is not, it's not easy to identify, but computers can easily identify it. And here is another graph which shows it, and it's the same. This is for ionized calcium. It's much easier. This is titanium oxide. It's very nice. You can identify its strength against temperature relationship. So there are many spectral types. This is not a single spectrum of a star. These are a group of spectrums. This is the O6 spectrum, this is the B0, this is the B6, this is the A1, this is the A5. We will understand now what is a spectral type, and this will introduce us to the HR diagram in the next lecture. So in each spectral type there are some absorption lines, there are parts with emission lines. Okay, and look at here, the emission is almost here, and as you move down, the emission starts to move at this place, which means that the temperature here is higher than the temperature here down at the M spectral type. And actually we will see that this relationship is there in the HR diagram. So how can we identify, how can we learn the spectral types? The spectral types are O, B, A, F, G, K, M. So there are many ways, many mnemonics, which is O, B, a fine girl kissed me, and oh boy, an F grade kills me, and only bad astronomers forget generally known mnemonics. Okay, so these are different ways to memorize the spectral types, and these are different spectrums, different profiles of the spectral types, and each profile is the wavelength here at the x-axis, and on the y-axis is the intensity, and the intensity can actually be performed at different scales. So what about the Doppler effect? What's a Doppler effect? Actually, the Doppler effect is it's well known in physics. It's like the effect of the ambulance. When an ambulance is coming towards you, a normal ambulance, you would hear it like wah, 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 but when it comes next to you, you can hear wah, 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 wah. And when it starts moving away from you, you'll start wah, 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 till the voice fades. So what's the reason for that? The reason is when the car is coming next to you, forward you, the waves of that sound will start to be compacted, will contract, because it's coming towards you, and when it's moving away from you, the wavelength starts to expand. So when the wavelength expands, the pitch is lower, so you hear it like that. And when it's coming towards you, the pitch is higher, because the frequency and the frequency became higher and the wavelength became less. It's the same totally for the light. When a star is coming next to you, the frequency of the star becomes higher, and when it's going away from you, the frequency becomes lower. So when it's coming next to you, there is a blue shift. All the spectrum shifts towards the blue region, and when the star is going away from you, the lines are shifted towards the red. And to identify the distance of a star, it's just very easy. You get the original lambda node and the new lambda, the new wavelength and the old original wavelength, and you make the difference between them, the delta, over the original lambda, which is the original wavelength, which is equal the radial velocity over the speed of light. Okay. So what's the radial velocity? When the Earth, a star, is moving away from it, this is the radial velocity. But it's not always the radial velocity. The velocity is not always radial, because the star can be moving not just in the radial vector of or the radial direction of the Earth. So finally, we can find that there is a Doppler broadening even in spectral lines that are absorption lines. And you can see that in the lines. The absorption lines should be just a line, but this is not what happens. What happens really is that there is a region away from the line, and this is caused due to the Doppler broadening, that this part is Doppler shifted. The element line was Doppler shifted towards the red and the blue. This is red shifted and this is blue shifted. So according to temperature, as the temperature increases, the atomic substances and particles starts to collide more and more, so there is more broadening in the lines, the absorption lines. But in the cooler stars, these lines are not as broad as the hot ones. So thank you. This was the end of our lecture, and I hope you enjoyed it.